Welcome to our YouTube channel. Today's topic for discussion is the ultimate rule breaker of the universe, the Tachyon. I want you to start off by just, imagining something for a minute. Picture a mirror universe living right alongside our own.
Okay, I'm with you. A parallel reality.
Yeah, but in this hidden universe, the fundamental rules of reality, like the physical laws you and I just completely take for granted, they are completely flipped upside down. It's this place where losing your energy makes you go infinitely fast, and trying to slow down requires an infinite amount of power.
I mean, it really sounds like the plot of a late-night sci-fi movie. But what we are actually describing here is a very concrete mathematical reality.
Right, it's not just made up.
Exactly. It's a
Wow.
reality that sits perfectly hidden inside the very equations that govern our own universe. So our goal for today's deep dive is to explore exactly that anomaly. We're going to really plunge into the mind-bending physics, the causality-shattering paradoxes, and the real-world hunt for this thing.
Because it's a particle that permanently lives faster than the speed of light.
Right. Yeah, that's the core of it. We are cutting entirely through the pop culture stuff to look exclusively at what the hard, unforgiving math and the actual laboratory experiments tell us.
Which is wild because you've always been told, like probably since grade school, that nothing goes faster than light, that it's the absolute unbreakable speed limit of the cosmos. But today, you'll learn why the math actually leaves a back door wide open for something that does exactly that.
To really understand that back door, though, we have to start by examining the wall itself. Like, before we can break the universe's ultimate speed limit, we need to understand exactly how that barrier is built.
Because it isn't just a suggestion, is it?
No, not at all. It's a structural feature of reality,
Yeah.
both mathematically and physically.
And the foundation for that wall was basically laid back in 1905, right? When Albert Einstein drops special relativity on the world and completely rewrites the rules.
Right. He essentially proved that space and time are not these separate, independent things ticking away in the background. They are woven together into a single, dynamic fabric called space-time.
Space-time, yeah.
And the absolute cornerstone of this entirely new framework is his equation for energy. When most people think of Einstein's energy equation, they immediately picture E equals mc squared.
Energy equals mass times the speed of light squared. It's literally the most famous equation in history.
It is. But a crucial detail that often gets overlooked, especially in popular science, is that E equals mc squared is actually only half the story.
Wait, really? Only half?
Yeah. Physicists actually refer to it as the rest energy equation. It only works perfectly if the object you are measuring is sitting completely, absolutely still. Its velocity literally has to be zero.
Okay, but the universe is super dynamic. Like things are constantly moving, planets orbit, rockets launch. So what happens mathematically when you take an object with mass and you actually give it velocity?
Well, the rest energy equation just can't handle that on its own. The moment an object starts moving, you have to use Einstein's full relativistic energy equation.
And that's where it gets complicated.
A little bit, yeah. In this full version, the total energy of an object equals its rest mass times the speed of light squared. So that's your normal E equals mc squared on the top. But then that entire top half is divided by a very specific mathematical denominator.
Right. And I know throwing complex math into an audio deep dive can be tough to visualize. So let's walk through this part slowly, because this specific denominator is the key to the entire speed limit, right?
It absolutely is. You divide by the square root of 1 minus the object's velocity squared over the speed of light squared. Let's just focus on that bottom part.
The square root of 1 minus a fraction. And that fraction is your speed squared divided by light speed squared. So let's say I'm in a spaceship, right? And I fire the thrusters and start accelerating.
Okay, so as your velocity climbs and gets closer and closer to the speed of light, look at what happens to that fraction. As your speed approaches light speed, that fraction, your speed over light speed, gets closer and closer to exactly 1.
Because the top and bottom numbers are becoming the same. And if that fraction gets closer to 1, then the equation demands we subtract it from 1. So 1 minus something very close to 1 leaves you with the number getting closer and closer to 0.
Right, which triggers a fundamental rule of mathematics. As the denominator of a fraction shrinks and approaches 0, the total value of that fraction skyrockets toward infinity.
Wow.
Translated into physical reality, this means that as your spaceship gets closer to the speed of light, the total energy required to keep accelerating it approaches infinity.
The analogy that really helped this click for me was thinking about pushing a broken down car. Like imagine you are trying to push a car to reach the speed of light.
That's a great way to visualize it.
But because of the rules of relativity, the faster the car rolls, the more its relativistic mass increases. It effectively gets heavier and heavier. So by the time you manage to push this car to 99% of the speed of light, the car has become almost infinitely massive.
Yes, and because of that, it would take an infinite amount of energy to push it that final 1%. Literally more energy than exists in all the stars and galaxies combined.
That is just mind-blowing.
That exponential requirement for energy is the exact mechanism of the light speed barrier. It's an asymptote. Because of this, physicists classify all normal matter as class I particles, also known as tachyons.
Tachyons, that basically means normal stuff, right?
Right. Tachyons or bradyons. These are particles with a squared mass greater than 0. You, me, the Earth, we are all made of tachyons, and we are forever doomed to travel slower than light. The math absolutely forbids us from crossing that line.
And then there are class 2 particles, right? The luxons.
Correct. Class 2 particles, or luxons, are completely massless. The most famous example is the photon, the particle of light.
So because they have 0 mass, they don't have to deal with the heavy car problem.
Exactly. Because they have 0 rest mass, the rules change. They don't just have the ability to travel at the speed of light. They are literally mandated by the laws of physics to travel exactly at the speed of light from the moment they are created.
Okay, so looking at this structurally, the speed of light isn't just a technological limit. Like, it's not about building a better rocket engine. It's an infinite mathematical wall.
That's the perfect way to summarize it. Normal matter can push up against the left side of this wall forever, but it can never, ever cross it.
But reading through the historical context, this is where the theoretical physicists started getting a little rebellious. Like, if it's just a wall preventing us from accelerating through the barrier, the obvious question is, what if something bypasses the acceleration part entirely?
Right, because the math unequivocally states that normal matter can never accelerate across that boundary. But the equations do not explicitly state what happens if a particle doesn't have to cross it.
Right. What if it's just born on the other side?
Exactly. What if, theoretically, a particle came into existence already moving faster than light?
It's basically the ultimate game of what if. And physicists started playing this game a long time ago, didn't they?
They did, yeah. The very first whispers of this idea were attributed to the German physicist Arnold Sommerfeld. But the rigorous modern physics treatment began with a highly influential 1962 paper called Meta-Relativity.
That was by George Sudarshan, Alexa Belaniuk, and Vijay Deshpande, right?
Yes, those three. And then a few years later, in 1967, Gerald Feinberg formalized a lot of these radical concepts and actually coined the term we use today, tachyon. He derived it from the Greek word tachys, meaning swift.
Okay, so Sudarshan and his team basically looked at Einstein's unbreakable barrier, and they decided to just forcefully plug a faster-than-light speed into the energy equation just to see what would happen.
They wanted to see if the math would break or if it would adapt. Let's actually run that exact experiment right now.
Let's do it.
Assume we have a hypothetical particle created moving at exactly twice the speed of light. Its velocity is 2c. So let's look at our denominator again, the square root of 1 minus velocity squared over the speed of light squared.
Okay, so if the velocity is 2 times the speed of light, then velocity squared gives us 4 times the speed of light squared.
Right.
And if we divide that by the speed of light squared on the bottom of the fraction, they just cancel out, which leaves us with just the number 4.
Exactly. So now our denominator is the square root of 1 minus 4, which means you are asking the equation to calculate the square root of -3.
And this is where the system completely crashes, because you can't take the square root of a negative number using normal numbers. 2 times 2 is 4, and -2 times -2 is also 4.
Right. It creates a state that requires what mathematicians call an imaginary number, which is always denoted by the letter I.
So the denominator instantly becomes imaginary.
It does. And for any normal particle, this fundamentally breaks the equation. It outputs an imaginary total energy, which is a meaningless concept in the physical universe. You literally cannot measure an imaginary joule of energy.
See, when I first read this part, my immediate reaction was extreme skepticism. Like, if we are forced to invent something called imaginary math just to make the concept work, doesn't that inherently mean it's totally fake?
That is a very common and highly intuitive reaction. The word imaginary carries a lot of baggage, but in advanced mathematics, an imaginary number isn't fake at all.
It's not.
No, it is a very rigorously defined mathematical tool. Electrical engineers use them every single day to calculate alternating currents in the power grid. Quantum mechanics relies heavily on complex numbers to describe real electrons.
Oh, wow. I didn't realize they were used in the real world like that.
They are. So generating an imaginary number doesn't mean the physics is fake. It just means we are entering a different mathematical domain.
Okay. I can accept that imaginary numbers have practical applications. But we still have an equation outputting an imaginary total energy for this particle. How did they fix that crash so the math makes physical sense?
The solution is incredibly elegant. They realized that to get a real, measurable total energy output, you have to balance the equation. If the denominator is generating an imaginary number, then the only way to cancel it out is if the particle's rest mass, the numerator sitting on top, must also be imaginary.
Oh, wow. So the math forces the mass to adapt. The particle has a mass of some number multiplied by I.
Exactly. And because it's traveling faster than light, the denominator is also a number multiplied by I.
And they just cancel out?
The I on the top and the I on the bottom perfectly divide out. They cancel each other completely. What you are left with is a completely normal, real, positive total energy and momentum.
That is a staggering loophole. It introduces the final category, right? Class 3 particles.
Yes. If a theoretical particle possesses an imaginary rest mass, it can move faster than light, and those two imaginary properties perfectly negate each other.
It's kind of like finding a grammatically correct sentence in a foreign language that describes something totally alien. The concept is weird, but the grammar itself is flawless. Einstein's math doesn't actually forbid tachyons from existing.
No, it doesn't. It actually provides a perfect, elegant framework for exactly how they would operate if they did exist, which opens the door to a really fascinating thought experiment.
Right, because mathematically establishing that it can exist is only the first step. The next question is, what would it actually look like?
Exactly. If you could isolate a class 3 particle in a laboratory, how would it behave?
And according to the sources, the behavior is totally inverted. It's like looking through the looking glass. Let's break down the rules of the fast lane. We established that for normal matter, adding energy increases speed, right?
Yes, you push the gas pedal, you burn more fuel, you go faster. But for a class 3 tachyon, that relationship is completely backward. The math dictates that if a tachyon loses energy, its velocity actually goes up.
Which totally defies every instinct we have. If I go back to the car analogy, it's like driving a vehicle that only accelerates when you slam your foot on the brake.
Yeah, or a car that gets faster and faster the more the gas tank drains. The emptier the tank, the more violently it accelerates down the highway.
That is so deeply counterintuitive.
It is, but it's mathematically sound. And if we follow that logic to its extreme, we reach a state physicists call the transcendent tachyon.
Transcendent tachyon, what does that mean?
Well, consider what happens if this particle continues to lose energy until it has no energy left at all. What if its total energy hits absolute zero?
Following the inverted rules, if losing energy means speeding up, then hitting zero energy would mean hitting infinite speed.
That is precisely what the equations output. A zero-energy tachyon occupies a state of infinite velocity, and the implications of that are staggering, particularly regarding momentum.
How so?
A transcendent tachyon would be capable of transferring momentum instantaneously from one point in the universe to any other point without transferring a single joule of energy along with it.
Wait, how is that even physically possible to visualize? Instantaneous momentum transfer without energy transfer.
The closest analogy we have is the theoretical concept of an infinitely rigid body. Imagine an infinitely rigid stick that is a light year long.
Okay, I'm picturing it.
If you push on your end of the stick, the other end moves instantly, transferring your push exactly at the same moment, regardless of the distance. The transcendent tachyon acts as an instantaneous momentum courier across spacetime.
Okay, that is crazy. So that's what happens when it loses energy. What happens when we try to add energy to a tachyon? Like, what if we try to slow it down?
Well, adding energy decreases its velocity. But here we run into the mirror image of the light speed barrier. Just as a normal particle needs infinite energy to reach the speed of light from below, a tachyon would require an infinite amount of energy to slow down and reach the speed of light from above.
So the speed of light isn't a ceiling for them, it's an impenetrable floor.
Exactly. The speed of light is the absolute, unbreakable boundary separating our two realms. Normal matter can never rise above it, and tachyons can never drop below it. They are forever locked in the superluminal domain.
But locking them in that superluminal domain introduces a massive, explosive problem, doesn't it? Because these particles are moving faster than light through the empty vacuum of space, and we know things get very violent when particles exceed the local speed of light.
You are referring to Cherenkov radiation, which is a critical piece of the Tachyon puzzle.
Yeah, let's talk about that.
To understand it, we need to look at normal physics first. While nothing can travel faster than C's in a perfect vacuum, light actually slows down when it travels through a medium, like water or glass.
Right, light is slower in water.
Because of that, it's possible for a normal particle, like an electron, to travel through water faster than light travels through that same water. When this happens, the particle creates a shock wave.
It's essentially an electromagnetic sonic boom, right?
Yeah.
And it manifests as a distinct blue glow.
Yes, that is Cherenkov radiation. For anyone who has seen footage of the core of a nuclear reactor underwater, that intense blue light, that's the electrons getting kicked out faster than light can move through the cooling water.
Okay, so let's apply this to our tachyon. A tachyon is constantly moving faster than the absolute speed of light in a perfect vacuum.
Right. And if a tachyon possesses an electric charge, the laws of electrodynamics dictate that it will constantly emit Cherenkov radiation just by moving through empty space.
But wait, emitting radiation means the particle is losing energy. It's radiating its energy away. And we just established that when a tachyon loses energy, it speeds up.
And there is the paradox that threatens to destroy the universe. If a charged tachyon emits Cherenkov radiation, its energy drops. Because its energy drops, it accelerates. At this new, higher velocity, it emits more radiation, losing even more energy, which forces it to accelerate even faster.
It's an infinite runaway reaction.
It is a catastrophic feedback loop. Within a fraction of a microsecond, the tachyon would accelerate toward infinite speed, bleeding out an infinitely large amount of energy into the vacuum. Space would violently erupt with spontaneous energy release.
Which obviously isn't happening. I mean, I can look out the window and verify that the universe has not boiled over into a blinding blue flash of infinite energy. Space is mostly dark.
Therefore, theoretical physicists had to draw a very firm line in the sand. If these particles do exist in our universe, they absolutely must be electrically neutral.
They cannot possess an electric charge.
Exactly. The math clearly shows the universe would be wildly unstable if they did.
Okay, so let's summarize the ghost particle so far. We're looking for a completely neutral particle with an imaginary rest mass, permanently moving faster than light and speeding up whenever it loses energy.
That's the profile.
It's incredibly weird. But reading the literature, the infinite speed and runaway loops aren't actually the reason mainstream physicists despise tachyons. The math they can handle. The real reason they hate tachyons is what they do to time.
Yes. Time is the ultimate casualty of the tachyon. To understand why physicists recoil from these particles, we have to go back to special relativity.
Okay, let's go back to Einstein.
Relativity dictates that time is not absolute. It is relative to your frame of reference. How you experience time depends entirely on how fast you are moving relative to the things around you.
Time dilation, right. The faster you move, the slower time ticks for you.
Yes. But when you plug a faster than light speed into the Lorentz transformations, which are the equations that translate different frames of reference, you get a devastating result.
What happens?
A mathematically unavoidable consequence of relativity is that if a particle moves faster than light, there will always be a valid frame of reference where that particle appears to be moving backward in time.
Hold on, let me make sure I'm visualizing this correctly. Let's say I'm standing still on a planet, and I watch a tachyon zip by me from point A to point B. To me, it just looks like a really fast particle moving forward in time. But to an astronaut flying past me in a spaceship at a high speed, the math says that the astronaut would observe that exact same tachyon moving from point B to point A, traveling backward through time.
That is correct. In the astronaut's frame of reference, the tachyon arrives at its destination before it ever leaves its source.
That is just broken.
And because relativity states that all inertial frames of reference are equally valid, both observations are true. And this creates an existential crisis for causality.
Because causality is the ironclad rule of physics. It's the bedrock of logic. A cause absolutely must happen before its effect. You drop a glass, then it shatters.
Right, the shattering cannot precede the dropping. But if tachyons can be observed traveling backward in time, they provide a mechanism for effects to precede their causes.
This logical nightmare was formalized in a famous thought experiment, right? The tachyonic antitelephone, or the Tolman paradox.
Yes, named after Richard Tolman. The antitelephone is a brilliant illustration of causal violations using superluminal signals.
It's probably my favorite part of this entire deep dive. It's the ultimate brain breaker. Let's walk the listener through the text message to yesterday's scenario.
Let's do it.
Imagine I have a futuristic tachyon transmitter sitting on my desk. Because we know tachyons can move backward in time relative to moving frames, I can use it to send a text message to myself. But the message won't arrive tomorrow, it will arrive 1 hour ago.
You are establishing a localized, closed time loop.
Exactly. So I send a text to my past self, and the text reads, "Hey, when you receive this text, immediately take a hammer and smash the transmitter on the desk so I can never send this text."
Okay, let's follow the timeline. Your past self receives the message an hour ago. Following the instructions, your past self picks up the hammer and completely destroys the Tachyon transmitter.
So it's in pieces.
Therefore, 1 hour later, when the time comes to send the original message, the machine is already destroyed. You do not have a machine to send the message.
And here is the paradox. If I didn't have the machine to send the message, how did my past self get the message telling me to smash it? Who sent the text?
Completely shatters the fundamental grammar of reality.
It really does. It's not just a physics problem. It's a breakdown of free will and logic. You can't have a universe where the effect actively prevents its own cause.
It is an insurmountable logical nightmare. And Feinberg and Sudarshan were acutely aware of this massive flaw. They knew the wider physics community would reject the theory outright.
So they tried to fix it, right, with the reinterpretation principle. How did they think they could possibly work around a text message from the future?
They relied on a quirk in the math. They argued that the mathematical description of a tachyon with negative energy moving backward in time is perfectly identical to a tachyon with positive energy moving forward in time.
They're completely indistinguishable equations.
Precisely. So they proposed a rule. Any observer who thought they saw a tachyon moving backward in time with negative energy would simply reinterpret that event.
Reinterpret it how?
They would mentally flip the signs. They would perceive it instead as a normal, positive energy tachyon moving forward in time, just traveling in the opposite direction. Instead of seeing a particle arriving from the future, they'd interpret it as a particle they were emitting into the future.
Okay, I have to push back hard on this. When I was reading their proposal, it felt incredibly flimsy. I understand that flipping the signs balances the math of the negative energy states.
It does fix the math.
But changing the label on the particle doesn't actually fix the anti-telephone paradox, does it? If I still smash the machine before I send the text, it absolutely does not matter if we reinterpret the particle.
You are entirely correct to push back.
The macroscopic causality is still broken. I'm forcing you to admit that this reinterpretation principle doesn't actually solve the logical nightmare at all. It just hides the math.
And the modern physics community completely agrees with you. The reinterpretation principle is widely considered to be a mathematical sleight of hand. It elegantly resolves the negative energy issue, but it utterly fails to save macroscopic causality.
Because the timeline is still scrambled. You can't just slap a new label on it and fix the timeline.
Exactly. You cannot formulate consistent initial conditions for a universe where information moves like this. In a normal universe, a cause and an effect are connected by a time-like interval.
Let's define a time-like interval for the listener because this is a crucial distinction.
A time-like interval means that there is enough time between event A and event B for a slower-than-light signal to travel between them. It means A has the physical capacity to influence B.
So if I throw a baseball out a window, the throwing and the shattering are separated by a time-like interval.
Yes, but tachyons don't obey that rule. Tachyons connect events by what are called space-like intervals.
And a space-like interval means the distance is too vast, right?
Right. It means the distance in space is so vast and the time between them is so short that not even light could travel from event A to event B. In our normal universe, event A absolutely cannot be the cause of event B.
They are causally disconnected.
But tachyons traverse space-like intervals. This means the chronological order of events isn't fixed. It can be scrambled depending on how fast an observer is moving.
So one person sees A cause B, and another sees B cause A.
And when you allow that, the foundation of physics crumbles. Probability conservation fails. The predictive power of quantum mechanics unravels. It is a theoretical dead end.
So if the idea of superluminal bullets flying around creating time loops is a dead end, you'd assume physics just threw the tachyon in the trash. But they didn't. They just shifted the definition.
They did.
We basically moved from thinking about bullets to thinking about mattresses.
That is an excellent analogy. Modern physics shifted away from classical particles and developed quantum field theory, or QFT.
Let's break down QFT simply. The universe isn't just empty space with hard spheres zipping around. Instead, it's filled with invisible fields. Think of an endless ocean or a giant mattress.
Every fundamental particle has its own field. There's an electron field, a photon field. And what we perceive as a physical particle is actually just a localized vibration, a ripple in that specific field.
You hit the mattress, and a ripple moves across it. That ripple is the particle. So how does the tachyon fit into this mattress?
In QFT, the concept of an imaginary mass takes on an entirely new meaning. It no longer implies a little physical bullet flying faster than light. Instead, having an imaginary mass means that the field itself is fundamentally unstable.
Okay, let's unpack this instability. In the sources, they describe an unstable field as sitting at a false vacuum.
Yes.
I pictured this using a bowling ball. Imagine a mountain with a perfectly sharp peak. You take a heavy bowling ball and balance it meticulously on the absolute tip of that peak.
Mathematically, the ball is at rest. It's perfectly balanced.
Its velocity is 0, but it is in an incredibly unstable state. We call this peak the false vacuum. It's theoretically balanced, but what happens if there's even the slightest microscopic breeze?
The ball immediately rolls off the peak. It plunges down the side of the mountain until it reaches the lowest possible point in the valley below.
And once it's in the valley, it stops. It finds its lowest resting point. The valley is the true vacuum. It's finally stable.
That is the perfect visualization of tachyonic instability. In QFT, a tachyonic field is that bowling ball perched on the peak. It is mathematically defined by having an imaginary mass, which just signifies its extreme instability.
So it won't stay at the peak.
You cannot stay at the peak.
Yeah.
It will spontaneously and violently roll down to the lowest energy state in the valley. And this isn't just some abstract concept. This tachyonic instability is the exact mechanism that built our reality.
Because we are talking about the Higgs mechanism, right? The thing that gives matter its mass.
We are. The most famous tachyonic field in physics is the Higgs field. In the incredibly hot fractions of a second just after the Big Bang, the Higgs field was sitting at that false vacuum peak.
It was, strictly mathematically speaking, a tachyonic field.
Yes, it possessed an imaginary mass. But as the universe expanded, it rapidly cooled. And as it cooled, the conditions changed. The breeze hit the bowling ball.
And it rolled down the mountain. The Higgs field plunged down to its lowest energy state in the stable valley. Physicists call this rapid transition spontaneous symmetry breaking.
Exactly.
Let's explain how that roll actually creates mass, because spontaneous symmetry breaking is kind of a dense term. How does settling into a valley give an electron its mass?
Think of the field in the true vacuum valley like a thick syrup that now permeates all of space. Before the roll, space was empty of this syrup, and particles like electrons zipped around at the speed of light, entirely massless.
But once the field settled into the valley, the syrup was everywhere.
Right. Now, as an electron tries to move through space, it wades through this pervasive Higgs field, it interacts with the syrup, that interaction creates drag, and that resistance is what we perceive and measure as mass.
So wait, if we trace the logic back, without this violently unstable tachyonic state in the early universe, the Higgs mechanism would never have occurred.
The field wouldn't have rolled down the mountain.
And without the syrup, the electron wouldn't have mass. Atoms could never form. You, me, the Earth, none of it would exist.
The universe would just be a chaotic soup of massless particles flying eternally at the speed of light.
Oh.
So while the time-traveling particle might be a phantom, the math of the tachyon literally built the physical structure of our reality. We owe our existence to a tachyonic field.
It completely reframes the entire topic. It takes it from sci-fi nonsense to the foundational bedrock of existence. And this concept pops up in string theory too, doesn't it?
It did, quite famously. It caused a massive crisis. The original version, bosonic string theory, was developed in the late 60s. It was a beautiful framework where fundamental particles were tiny vibrating strings.
But they quickly realized it had a catastrophic mathematical flaw. The equations predicted tachyons.
And in string theory, if the theory predicts a tachyon, it means there's a tachyon vibration. It means the fundamental fabric of the theory, the underlying space-time itself, the D-brain, is ripping itself apart.
The theory was essentially screaming, I am unstable, my bowling ball is on the mountain.
Yes. It meant bosonic string theory could not describe a stable universe like ours. This forced the evolution of the theory into superstring theory, which incorporated supersymmetry.
Supersymmetry? How did that fix it?
It paired every particle with a heavier partner, and the math of these partners perfectly canceled out the instabilities. The tachyon was mathematically eliminated, allowing string theory to describe a stable vacuum.
Okay, so theorists have spent decades wrestling with tachyons. They tried to reinterpret them, they turned them into fields, they used supersymmetry to eliminate them. Theorists clearly hate the paradoxes.
They really do.
But experimentalists are an entirely different breed. An experimentalist knows you can't just rule something out because it gives you a headache about time travel. You have to actually look for it in the real world.
That is the core of the scientific method. If the equations explicitly allow for a class 3 particle, you have to design an experiment to hunt for it. You have to ask the universe if it exists.
And physicists have been hunting for a long time. Let's transition into the real-world search. Where did experimentalists even start looking for something that goes faster than light?
One of the earliest attempts was in 1968 by Torsten Alvager and Michael Chrysler. Remember our discussion about Cherenkov radiation? If a tachyon has an electric charge, it will emit a massive amount of light in a vacuum.
The electromagnetic sonic boom. The bright blue glow.
So they designed an experiment to search for charged tachyons by firing incredibly high-energy photons at a solid lead target. They hoped the intense collision might spontaneously create tachyon pairs out of the vacuum.
And they surrounded the area with detectors to look for the flash.
Yes, highly sensitive photomultiplier tubes.
Yeah.
And what did they find? Absolute silence, a completely null result.
But we kind of knew that was going to happen, right? We established earlier that if charged tachyons existed, the universe would have boiled over long ago.
True. Looking for charged tachyons was always a massive long shot. The real prize would be neutral tachyons.
But neutral particles don't emit that blue light. So how do you detect an invisible particle moving infinitely fast?
You have to look for the hole it leaves behind. You look for what is missing from the system. It's an accounting trick. You balance the checkbook of a particle collision.
If the energy before the reaction is 100 and the energy after is 95, you know an invisible particle snuck away with 5 units of energy.
Precisely. In 1970, Charles Balte set up an accelerator experiment to search for neutral tachyons. They smashed particles together and tracked the energy of every visible particle. They were specifically looking for missing energy with a space-like signature.
Let's explain how they identify a space-like signature. How does missing energy look space-like?
In relativity, energy and momentum are linked. For normal matter, the energy component is always greater than the momentum component. But for tachyons, because of their superluminal speed, the momentum component is actually greater than the energy component.
So Balte's team was looking for a momentum deficit that was disproportionately huge. That's the undeniable fingerprint of a tachyon.
Exactly. And the result, another frustratingly null result, they found 0 events that matched the signature.
So accelerators weren't producing them. But scientists didn't stop in the 70s. They looked up at the sky, too, because cosmic rays hit the atmosphere from deep space, right?
Yes, cosmic rays hit the atmosphere and shatter atoms, creating massive showers of secondary particles. In 1988, Roger Clay decided to search for tachyons within these showers.
The logic here is so fascinating. Because tachyons travel faster than light, if a cosmic ray creates a tachyon, it wouldn't stay with the pack.
No, it would race ahead of the rest of the shower. It would hit the ground detectors on Earth before the main particle shower even arrived. You look for an anomalous precursor trigger.
Did Clay find any precursors?
There were some debated initial blips, but ultimately rigorous analysis showed absolutely no conclusive evidence. The precursor signals were just noise.
The sources also mention decay in flight. What's that?
A stable proton will basically last until the end of the universe. But if tachyons interact with normal matter, a perfectly stable proton flying through space could theoretically spontaneously emit a tachyon.
But if it emits a tachyon, it loses energy, and its internal structure changes, it decays. Have we ever seen a stable proton do that?
Never. Extensive observations have yielded 0 results.
Okay, we've walked through decades of null results. But we absolutely must talk about 2011, the opera debacle, because this was the moment the tachyon almost broke the internet.
It was monumental. Opera was a massive experiment studying neutrinos fired through the Earth's crust from CERN in Switzerland to a lab in Italy 450 miles away.
And what happened in September 2011?
The team made a shocking announcement. Their sensors measured the neutrinos arriving in Italy 60 nanoseconds faster than if they had been traveling at the exact speed of light.
They literally claimed to have found a faster-than-light particle, a real tachyon. The news cycle went crazy.
The physics community went into absolute overdrive. Theoretical physicists frantically published papers trying to use tachyonic wave packet theories to explain the data.
And this is where I have to call out the theorists. They spend decades saying they don't believe in tachyons because the math is ugly. But the second the data suggests it,
They secretly have all these elaborate tachyon series completely ready to go. It's true. Breaking relativity is the ultimate puzzle, but the panic was short-lived.
because it wasn't a tachyon taking a shortcut. It turned out to be a hardware glitch, a loose fiber optic cable.
A deeply embarrassing loose cable. It introduced a delay in the timing calibration. Once tightened, the 60 nanosecond anomaly vanished. Einstein remained undefeated.
So we have null results across the board. Does that mean we've definitively proved tachyons do not exist?
This is a profoundly important philosophical question. You can never perfectly prove a negative. You can't design an experiment that proves something doesn't exist anywhere in the universe.
It's like searching for your keys. You can say they aren't in the kitchen, but you can't logically prove they no longer exist unless you search the entire universe simultaneously.
Exactly. Just as we can't rule out intelligent aliens, we cannot definitively rule out extremely weakly interacting neutral tachyons. They remain scientifically unsettled.
So the tachyon remains the enfant terrible of physics, a rebellious child allowed by the grammar of Einstein's equations, but rejected by the logic of cause and effect.
But the concept survives as a vital mathematical quirk in QFT. The tachyon field gave matter its mass.
We owe our lives to a ghost. But before we sign off, I know you have one final mind bender for the listener.
I do. If tachyonic fields are a fundamental part of nature, models suggest that even the absolute ground state of our universe, the cold vacuum of space we consider stable, might actually be fundamentally unstable to tachyon emission over vast timescales.
Unstable? What does that mean for us?
Remember the bowling ball. What if the stable universe we live in is just a temporary ledge on a much larger mountain? What if a brand new tachyonic instability is secretly boiling right beneath the surface, waiting to spontaneously break the symmetry again?
If that happens, the laws of physics rewrite themselves and our reality is wiped out at the speed of light. That is a terrifying and brilliant place to leave it, an invisible time bomb ticking in the math. Thanks for waiting till here. Please do like, subscribe, and comment.